class. In this section, we will continue our discussion on inventory control models. We'll discuss the purchase cost of inventory items. So when we look at the total cost of the inventory, it has to be written to include the cost of the purchased items. And so here we have our variables associated with our formula. We have the cost of the items per unit and the annual demand. So at delivery times, we may want to know the average dollar level of the inventory. And here we have the average dollar level is equal to the cost per unit times the quantity that we need to order divided by 2. So here are a couple of other items that of note. Inventory carrying cost expressed as an annual percentage of the unit cost or price of the inventory. And so now we introduce a new variable which we call I, which is the annual inventory holding charge as a percentage of the unit cost. So the cost of storing the inventory for 1 year is then the cost of holding times the annual inventory holding charge times the charge for the item. I think I said that wrong. The cost per holding is equal to the annual inventory holding charge, I, times C, which is our cost. Therefore, when we do our formula, we end up, which is the most important thing, is that the economic order quantity, Q star, is equal to the square root of 2 times DC, C associated with our ordering costs, divided by our cost for holding. Okay, so what is that the economic order quality model does? It assumes that all the values are basically deterministic, and we know that that is fixed. We know what they are. So some of these values may change, and when we look at determining the change, as we noted in an earlier class, we call it sensitivity analysis. And so here we have the formula for the economic order quantity. In our Sumco pump example, we computed the economic order quantity to be 200 units. So if the ordering costs were increased 4 times, that is, if it goes from $10 to $40, what happens? So when we substitute the value of 40 in for 10, we get 200 units. So what does that say? Well, we see that we increased it 4 times, but the economic order quantity only increased 2 times. So what does that say? Well, it is the square root of the value that the order increases by. For example, it increased by 4 times. The square root of 4 is 2. Therefore, the economic quantity increased 2 times. So now we look at reorder point. When is it that we want to reorder? That is a decision that has to be made. So we have the time between placing an order and receiving the order is called the lead time or the delivery time. And we want to find the reorder point is simply the demand that we have per day times the lead time that it takes us to get them. The demand for Promcom's computer chips is 8,000 per year. The daily demand is 40 units. Delivery takes 3 working days. So the reorder point simply becomes the daily demand, which is a deterministic value, and the lead time, which we know. So we have 40 times 3. So here is our reorder point. When we get down to 120 units, that's the time it is to reorder. Here are reorder point graphs. And as we discussed this graph before, we know that we have the optimum quantity that we have on hand. And when our stocks gets down to 0, we have nothing. Well, we want, if we know the lead time, then we can know when that reorder point is to keep us from getting to 0. Because remember, if we get down to 0, we want to automatically be able to go back to our... Okay, so here's what we have. We have the economic order quantity without instantaneous receipt assumptions. Okay, so when the inventory accumulates over time, the instantaneous receipt does not apply. So the demand rate must be taken into account, and we have to revise our model. And when we revise our model, the model is called the production run model. And so as you see from the graph below, what happens? You have your maximum inventory, and then you reach up to your maximum inventory, then it goes down over time, and then it comes back up. Right, so we want to look at the annual carrying cost for production run model. In this model, the setup cost is going to replace our ordering costs. And then we have our variables, the pieces to our puzzle, as listed. So, well, what's our maximum inventory level? And here you see the formula for our maximum inventory level and the associated variables. So at the end of the day, when we look at our maximum inventory level, we look at the number of pieces that we order, Q, times 1 minus the daily demand rate divided by the production rate. And since the average inventory is only 1/2 the maximum, we come up with the formula for the average inventory, Q divided by 2, and then again, to find the annual holding cost, we take Q and divide it by 2 and multiply it times 1 minus the demand over the production times the cost for holding. So when the setup cost replaces the ordering costs, when the model is produced over time, here we have the other two equations. We have the annual setup cost, which is simply the demand divided by the quality times the cost of setup. And that's going to replace the annual ordering cost in our previous formula in our economic ordering model. So now we can determine the optimum production. And as you see, the economic ordering quantity, as we expressed before, Q star, is equal to the square root of the equation presented below. So, in other words, we're going to get all these pieces. We're going to be able to pull all these pieces. All we have to do is put them into our model, and then once we put them into our model, we can compute our economic order quantity. And this is indeed a mathematical model that says that this is how I get my economic order quantity, or Q star. So here's a summary of the equations that we need. We have the annual holding cost equation. We have the annual setup cost equation. And we have the optimal production quantity Q star equation. An example, we have Brown Manufacturing Company, and then in this example, we're given our annual demand, our set of costs, our carrying costs, our daily production rate, and our daily demand rate. So the question becomes, how many units should Brown produce in each batch, and how long should the production part of the cycle last? So we have our equations, and we simply put in our values into our equation, and we do the math, and we find the answer to our two questions, that they should produce 4,000 units and that the production cycle is 50 days. Of course, we can let Excel do the heavy lifting, and we want to go to our Excel model and look up our economical order quantity as we've done before. When we do that, we want to look at the reorder point. And in this case, we're also going to check the graph. And when we do that, we get the output that we're looking for. And if you take a look at this example, when we do our QM for Windows and we bring up our model, we have to make sure that our formulas match up to the formulas here. So you're going to put in this data, and once you put in this data, these formulas are going to be calculated, and these are the same formulas that we looked at before. And so in your cells in your Excel program, you need to make sure that these are appropriate, and if they're off by 1, you might want to change that. For example, in the one I showed you before, there was an extra space introduced here, which causes my demand rate to be B8, and everything else shifts down. So if that does it for your formula, you have to make sure that these formulas make the appropriate shift. If not, you're not going to get the same numbers that are being calculated here. Okay, that does it for this section.